Ladies and gentlemen, welcome to this webinar. We're going to talk about things called process capability indices and PPM defects. And of course, that's a very wordy title, and many of you will only have turned up given that you know what those phrases mean and perhaps are involved in them, or have to use these phrases at your work or your place of study. But notwithstanding, we're going to go through what these phrases mean and how we can work on them, or how we can incorporate them into usually manufacturing or production processes to make sure we build high quality things that don't fail. And of course, this is largely about manufacturing and quality, but what a lot of reliability engineers don't like to admit is about 80% of so-called quality problems tend to originate during the design of something. And Fred has shared in the chat window the link to the guidebook for today. So let's focus on a really, really, really complex system and use that as an example for the discussion we're about to have. And that complex system is a loaf of bread. Now, this might not seem very complex, but actually it is. Making a loaf of bread involves a huge array of interactions between processes like yeast, fermenting, and getting the right number of ingredients right, making sure you don't have too much sugar, make sure you're having enough sugar, all those things that make a loaf of bread what we call chewable. And that is actually a genuine metric for bread. It's not just a subjective feeling you get once you chomp into a slice of bread. No, chewability is something we can measure, albeit in a relatively expensive way. When I say expensive way, we have to put a bit of bread under a probe and slowly test it. And of course, that bread can never be used again. So we lose ourselves one loaf of bread, and there is a little bit of time taken to get or measure chewability. But once we do, we can look at the chewability of a loaf of bread using the random hand of chewability. Now, I know some of the veterans will be familiar with this random hand, this hand that I use to represent random processes. I often use this hand to represent the random hand of failure. Well, sorry, I use this hand to represent the random failure process, I should say. A hand can't represent itself. In this case, the hand is being used to represent another random process, which is all the processes that need to work together to make a lovely, chewable loaf of bread. And we have things like LSLs or USLs, which are essentially the boundaries between what we say good bread is and bad bread is. LSL stands for lower specification limit. USL stands for upper specification limit. And at least semantically, these terms refer to the boundaries between good and evil, or good and bad. Anything outside those red lines you can see on the chart represent a bad loaf of bread, at least when we look at it from the perspective of chewability. And let's just say we run a bakery, and each one of these blue dots represents the chewability of a loaf of bread that we bake on any given day. Now, you might look at these blue dots and say, you know what? Looks like pretty much every one of these loaves of bread that we measured are within the USL and the LSI within our specification limits, which means they're all good. Well, up until a point, as a rule, when it comes to manufacturing processes and things like that, we don't ever want to have to deal with loaves of bread or any products which are close to specification limits. If they are, that means there's a pretty good chance that one of our loaves of bread or ball bearings or transistors is going to be outside the specification limit in the next batch of thousands we create. So this variation we see can be caused by any number of root causes. So, for example, we might have issues regarding how our bread is baked. But regardless, let's just say this is a ball bearing, and this ball bearing, the variation in our ball bearings special characteristic might then go on to lead to unreliability later on because that ball bearing isn't as close to the nominal value as possible. Or if we have tons of ball bearings that need to work together, which means that any deviation from the nominal value could then combine with deviations that other ball bearings have. That's what we call tolerance stack up, where essentially teeny tiny variations, especially if there's a tendency for the characteristic in question to be below or above a nominal value, we often get that tolerance stack up where all those components add up to create a huge gap or huge issue later on. And beyond that, when we have deviation or variation in key characteristics, we often just get undesirable products, those products which have sharp edges or make noises or squeak or rattle or don't taste as good or can't be used in harsh environments, etc., etc., etc. So even though every single one of these blue dots visually is within our specification limits, it doesn't mean that this is actually a good this is necessarily a good baking process. And when it comes to engineering, design engineers are notorious for putting absolutely no thought into appropriate specification limits. We always need to fight to improve the quality of the things we're baking or manufacturing. So ideally, we want to have the variation in a key characteristic looking like this. Now, a lot of people say, okay, so that's going to cost us lots of money. Why do we, if it's within the specification limits, then we're good. Any additional money we spend in reducing variation is money wasted. Well, those who know how to make quality products will fervently disagree. But beyond that, the reason why you want to have this sort of minimal variation in your products is because when your process does age, does drift, does change over time, every process does, if you have a teeny tiny variation in your products, then you're going to notice that this tight collection of dots might be slowly but surely moving towards the upper specification limit over time, which gives you early warning. So if you can see that your process is slowly drifting towards one of these specification limits, but the variation is so tight that you've got a lot of time before those products start to go outside the specification limit, what you are able to do is prevent a crisis where all hands are on deck. It's a level 5 code red emergency. We have tons of money thrown at the problem to create a solution which will hopefully get us producing again within the next 5 minutes. And usually those solutions don't last the test of time. If you can see that within 4 or 5 weeks, your bread's going to start to be outside specification limits because you're tracking this tight collection of blue dots moving, then you can slowly and calmly research, understand what's going on, and in the fullness of time, implement a corrective action, which is possibly the cheapest one out of all the solutions you've been able to survey, or at the very least, the most effective one for long-term stability. And that's what organizations who manufacture high quality things, they get to enjoy really high quality products and fast crisis-free production schedules. So that's what we're trying to get as a rule. Now, let's go back to that original variation. Now, one of the ways we often characterize the variation of things like bread chewability is with this bell curve here. Now, the bell curve is a curve that a lot of people have heard of, but actually don't know where it comes from. I've done a couple of webinars on where the bell curve comes from. And to summarize those conversations, the bell curve emerges when we have a random process, which is of itself the sum or aggregate of lots of other random processes. So, for example, human height. The height that human beings ultimately end up growing into is often described pretty well by a bell curve. The variation in human height is described pretty well by a bell curve because human heights can be seen as the sum of lots of other random processes that include genetics, diet, exercise, injuries, so on and so forth. And all those different processes add up. And we've been able to prove that when you have a random process, which is of itself the sum of lots of other random processes, we will always get the bell curve if we have enough of those random processes adding up together. And that's the same for manufacturing or baking as a general rule. It's not always the case, but we often see the bell curve in manufacturing and baking processes. But unfortunately, too many people assume that the bell curve describes the variation in something that's being produced, as opposed to actually confirming it first. But let's just say that in this case, we've confirmed through data analysis that these blue dots do appear to be well modeled by this thing called bell curve. Now, in the world of manufacturing, and in this case, bread making, We use this term capability or the term capable to describe the extent to which the variation in something is within the specification limits. So this process here, where those blue dots, those chewabilities of those loaves of bread that we're baking are more tightly condensed around a central or nominal value, this is what we call a process that is more capable. So the baking process that led to this minimal variation in bread chewability, and that variation was well within the specification limits, means that our process is more capable, which is where the term capability index comes from. The index to which, the number that essentially describes how capable your process is. The idea is the higher the number, the more capable your process is. And the capability indices have been used in a way to really simplify or summarize the quality of processes that we often use to manufacture things, including bread. So this process here, where we have more variation, the bell curve is shorter and fatter, is less capable, which means that it would have a lower capability index. Now, you can see that the capability index here, we have a symbol following it, which is an uppercase letter C followed by two lowercase letters PK. We often call this capability index, wait for it, CPK. Now, CPK is one of the most dominant capability indices, and for good reason. It's because it's really good at summarizing how capable your process is. But I often get asked, when is our CPK okay? Now, before I move on, can I get a show of emoji hands from the attendees who of you have heard of the CPK? I see a couple putting their hands up. Looks to me maybe a third, approaching maybe a half, maybe closer to a third. All right, so hands down. And now, can anyone who's ever heard of the phrase capability index now put up your hand? And I know that might not be the same people. Anyone who's heard of what's capability index? Roughly the same number. I'm guessing that roughly the same number of you who have heard or are aware of what a capability index represents have also heard of the CPK. Now, if you go to guidebooks or textbooks or standards, you'll often get guidance which looks like this. It tells us when our CPK is okay. And you can see here we have numbers. And apparently when we have two specification limits, that is where it's possible for our characteristic to be either too high or too low. So we have an upper specification limit and a lower specification limit. We have a bunch of numbers on the left-hand side, which tell us how, when our CPK is okay. On the other end, if we have one specification limit, then that means that whatever characteristic we're investigating, it's only bad if it's too high, or it's only bad if it's too low. It can, so for example, if you only have an upper specification limit on a particular characteristic, that might mean that we don't care how low it goes. In fact, maybe the lower it goes, the better. In some cases, you might have a specification limit for a surface coating. If the surface coating is at least a certain thickness, and you might only demand that the surface coating be greater than a certain number, then you have a lower specification limit. That's assuming you don't care how thick it is thereafter. Don't care how thick that coating is, as long as it's greater than a certain value or certain number or certain thickness, then that's a scenario where you have one specification limit. And so we have these guidebooks which give you these recommendations for what your CPK needs to be. You can see that if your CPK is less than 1, your process is not capable. If it's equal to 1, then it's barely capable. If it's equal to or greater than 1.33 for a 2 specification limit scenario, or a 1.25 for a one specification limit scenario, that's okay if it's an existing process. But if it's a new process, we need to demand higher specification, higher CPKs, and that's usually based on the premise that our new process will change quite quickly. If we haven't been observing it for a number of years, that's going to change quite quickly. So we initially demand a higher CPK, and we obviously demand higher CPKs for safety-related existing processes and the safety-related new processes. And then for those of you who have heard of or belong to the cult that is the Six Sigma group, they will advocate that the only CPK that's good is a CPK greater than 2. And so the CPK, essentially, all the CPK tells us is the extent to which variation is within those specification limits. Now, I've dealt with the definition of CPK in other webinars, and so what I can't do is go through a full description of what the CPK is, but I'll give you a little overview in this lesson, and we'll talk about what that means in terms of variation. Now, for those of you who are familiar with the bell curve, or any probability distribution for that matter, you can see here that I have shaded this bell curve with 3 regions. You can see there's sort of a dark orange region in the middle, and then there's 2 less dark regions either side of that dark region. And you can see there's another 3rd region of even lighter orange. What those regions represent are standard deviations away from the mean, or the middle. So the middle bit of our process, you can see the really dark orange, that represents a region that is within 1 standard deviation of the mean, the middle bit. The next shade down, that represents the region which is within 2 standard deviations of the mean. And the last really light region represents the region that is within 3 standard deviations of the mean. So a CPK essentially is based on how far away 3 standard deviations are from the mean and how that relates to the nearest specification limit. So if your nearest specification limit is exactly 3 standard deviations away from the mean, then you have a CPK value of 1. And on the right, you can see we have a little continuum where we have that little arrow or indicator showing that this process has a CPK value of 1 because the nearest specification limit is 3 standard deviations away from the mean. The higher the value, the better the CPK, the more capable the process. So if we improve process capability, maybe for our baking operation, our bakery looks at how to essentially better measure the ingredients going in, or they clean the sensors for the ovens that are there to that are supposed to be perfectly calibrated to make sure enough bread ferments and everything else. And then maybe after this program of quality improvement for bread making, we get a process which is way more capable. And in fact, you can see that in this case, when we reduce that variation, we now have a CPK value of 2. So remember, CPK is equal to 1 when the nearest specification limit is 3 standard deviations. A CPK in this case is equal to 2 if the nearest specification limit is exactly 6 standard deviations away. Hypothetically, if the CPK was 3, then the nearest specification limit would be 9 standard deviations away from the mean. So every unit increase in the CPK tells you that the nearest specification limit is now an additional 3 standard deviations away from the mean. So all the CPK does is essentially characterize how close the mean is to the nearest specification limit in terms of the number of standard deviations. And 3 standard deviations is 1 unit increase in the CPK. So let's go back to our CPK, which is equal to 1. Now this, remember, is what those numbers told us before as being barely capable. So even though every one of these blue data points appears to fall within the specification limits, as a rule, this is a barely capable process, at least by the definition or the table we looked at in the previous slides. So when is our CPK okay? Which one of those numbers do we choose? This is actually the wrong question. The reason being is because if we just blindly walk down the path of trying to find the right CPK or the goal CPK just so I could put it into a document and ask someone else to work towards that, we are setting ourselves up for failure. What we need to start asking ourselves is, what should my goal CPK be for each process characteristic? Now, what I'm going to do is going to unveil a bait and switch strategy for this webinar, which I'll make zero apologies for. And I'm going to start talking what might appear to be a very random deviation from the track of this conversation and start talking about reliability allocation. I need you to trust me. Reason being is because reliability allocation is actually a very similar process to what we should be going through when we are trying to come up with target CPKs for our processes. Now, don't forget, every one of our characteristics for our device or our product or a component usually needs to have its own CPK value. So, for example, the mass of the bread might need to have a goal CPK because you don't want it to be too big or too small. We know the chewability needs to have a CPK goal. Perhaps the number of slices or the thickness of slices, that needs to have a target or goal CPK. The reason being is because all these things are how our customers or users judge the quality or the value or the goodness of our loaf of bread. The same with the smartphone and everything else. Everything that our customer or user is going to essentially base their assessment on how good your thing is, that often needs to have a CPK goal during manufacturing. We often call those characteristics critical to quality characteristics. You don't want to have thousands of them because it becomes unwieldy. You just usually need to focus on the ones that sort of dominate the customer or user experience. And because of that, we need to understand that we can't just have extraordinarily high CPK goals for every single characteristic. Some characteristics are harder to achieve than others. And so that's why we start this conversation about reliability allocation, which I always start with the phrase, life is like a box of chocolates. And now a ton of you are even more confused than you were at the start of this conversation. But the reason I start with this phrase is because reliability allocation is like a delicious pie. Here is the pie of reliability that some of you veterans will be familiar with from my reliability allocation discussion. The idea is that at the start of a design process where you're trying to manage and stay on top of reliability, you usually start with the maximum amount of unreliability that you can allow your device to have. A higher quality and more reliable product can only have a much smaller pie. Designers actually like bigger pies. Smaller pies, well, everyone likes bigger pies. If you don't, there's something wrong with you. But if you don't like bigger pies, and this analogy is not going to work, but bigger pies are always better from a design perspective because it's always easier to design less reliable stuff. The smaller the pie, the harder it is to design something that meets that reliability target. So perhaps these should be called pies of unreliability. But nonetheless, hopefully the analogy is starting to stick. And let's just say that instead of manufacturing something, we're going to design my good old smart lock. And we say that the smart lock needs to have a service life reliability requirement of 95%. And that means that all these components, all these 17 components, 16 of them are different because we have 2 identical handles, need to work in a way that ensures that our smart lock has a 5-year service reliability that it is equal to or greater than 95%. Now, the dumb way to deal with this is to say to every single group or team responsible for each component that they now then have their own individual reliability target for each component of 95%. There's a huge problem with that. The problem with that is that because if you give these targets to the handle and the shaft and the spring and the clutch and the LED and the speaker, is that when these things come back together, it turns out that they will only, the smart lock where all 17 components have an actual reliability 95% means that the smart lock itself will only have a reliability of 42%. Reason being, essentially, is that you give 17 components, each of those 17 components a 5% chance of failing within a 5-year window. Well, you only need one of those 17 components to fail. And so the more ways you give your product to fail, the less reliable it is. And if every single one of those ways to fail has a 5% chance of occurring, then when those 17 combine, they actually create a much, much bigger system failure probability. And so when you have your pie of unreliability, you need to always rethink about how much pie you give everyone. You want to make sure that everyone has a slice of pie that when that thing is put back together, meets your, allows your thing to perform in a way that meets your system or product performance targets. Now, go back to our smart lock. So here are our 17 components, 16 of them are different. You can see that some of these components are going to be more challenging to manufacture or design than others. For example, you would suspect that the handle, which is 1.3 front and back, is going to be a much easier design challenge than the PCB 1.6 or the software. It also suspects that the LED is going to be a much less challenging design problem than the electric motor and the gear set. So we know that not all components are created equal. And so every single one of these 17 components, 16 of them are different, are going to have different scales or different levels of reliability design challenges. And so let's just say that we're able to come up with some sort of subjective number or scale to characterize how challenging each one of these components is going to be. And we often do this by getting maybe 4 to 8 people in a room. I often prefer doing it by just having those 4 to 8 people in a room. We talk about the design challenges. We go through this. Usually they have to be representative of the entire system. Then I ask them to anonymously score or anonymously pick a number between 0 and 10, 10 representing the highest characterization of design challenges, and 1, I suppose, not 0, but 1 representing the lowest. So that if someone says, you know what, I believe the PCB has a reliability design challenge score of 10, and that means that if the spring, I think, has a reliability design challenge of 5, that I expect the spring to have about half as many design challenges or reliability challenges as the PCB. And let's just say we can get these little columns to represent the design challenges of the 16 different components, 17 in total, because we have 2 handles. Essentially, these are what we call allocation factors, A subscript I. The idea is that the higher the number, the more challenging that thing is going to be to design to a reliable way. And for those of you who have seen my reliability and allocation lesson, this is a bit of revision. Essentially, what this equation here allows me to do is work out design goals for each one of these components. In this case, you can see the allocation factor A subscript I is the allocation factor for the ith subsystem or component. And you can see that we have the sum of all allocation factors for the system. This will then give us the goal, reliability goal for our handle, our PCB, or our LED, or our speaker, or whatever it is, based on our system reliability design goal. And the idea is that when we do that, we give these targets, these goals to each component in a way that allows them to, when they come back together, ensure that we meet our system reliability targets. So you can see here that the PCB appears to have the highest, the largest, or the biggest design challenges when it comes to reliability. So it has the highest allocation factor, where the speaker and LED appear to have the lowest or the smallest number of design challenges, which means that when we use those equations, this is what we get. We get these following individual component allocated reliability goals. You can see that they sort of had a bit of mirror effect. For example, we can see that the component with the highest allocation factor, that PCB, has the easiest or lowest reliability design goal target. So, and if we move across to the LED and the speaker, which people decided had the fewest reliability design challenges or the lowest allocation factors, they are the ones with the highest or most challenging goals, which makes sense. You don't want to give the most troublesome part of your system, the part of your system that's going to keep you up at night, the hardest goals to achieve. That's going to essentially burn through money, burn through time. Whereas if you essentially get your really simple components to carry the load when it comes to reliability, you save yourself a ton of time and a ton of money. Now, why am I torturing you guys with this nonsense discussion about reliability allocation when you were drawn to this webinar, no doubt, because we're going to talk about manufacturing stuff. Let's go back to this barely capable process. And let's look at this in greater detail. This is a process where we have a capability, or sorry, CPK, capability index score of 1. Now, if it's even less capable than that, then our process might look something like this, where we CPK has a value of 0.67, I should say. And that means that in this case, the nearest specification limit is only 2 standard deviations away from the mean. What that means in the real world is that a process with a CPK value of 0.67 can have up to 45,500 parts per million defective. So we're talking about almost 5% of our breads being loaves of bread, I should say, being defective or being too chewable or not chewable enough if our baking process is a CPK value of 0.67. If our capability index is 1, exactly 1, then we can have up to 2,700 parts per million defective. If our CPK value increases to, in this case, 1.5, then the statistics tell us that up to 6.8 parts per million will be defective. And if we have a CPK value of 2, then that tells us that we would expect up to 0.002 parts per million to be defective. And so this is something which is not often taught, that the CPK values are actually, for all intents and purposes, analogous to how many things are going to be defective once we produce them. So for those people who have heard of the CPK before, or capability indices, can I have a show of hands of people who were unaware that a CPK has also, for example, an accompanying parts per million defect rate, or at least another way of sort of characterizing the quantity of defective products you're going to manufacture. So I can see 1. So people who are unaware of the link between CPK, which is just a number we have defined, and the number of a precise number of defective things that we're going to create. Okay, so we've got a couple of people who are unaware that the CPK is essentially one way of characterizing how many defective things you're going to create if you know how to make that link. And you can see here we have a relatively straight line. It's not perfectly straight. On the horizontal axis, we have a uniform scale for CPK, but on the vertical axis, we have a logarithmic scale. So you can see that for every teeny tiny increase we have in CPK, we really reduce the number of defective components or parts or loaves of bread we're going to manufacture. So let's go back to our pies of unreliability, where in this case, we have to start with an open conversation about, what it is we're trying to do. What does good look like? Well, when it comes to manufacturing, we, in a way, can look at these pies in terms of pies of defects. If we can tolerate fewer defects, then our pie gets smaller. And because the defects, the enabled number of defects, or sorry, defects correlate with the CPK value, we can actually make these, look at these pies in terms of pies of CPK. So when you manufacture something and you might have 4 or 5 critical to quality characteristics, and each one of those critical to quality characteristics have upper and lower specification limits, so that if you take any product and any one of those characteristics, mass, chewability, color, whatever, if any one of those characteristics are outside specifications, then you have a defective product. So if it's not an average, it's every single time one of those CTQ, critical to quality characteristics, are outside of specification limits, that product is defective. It doesn't matter if your bread is the most chewable bread in the world, in a good way. If it's 50 grams below the lower specification limit for mass, it's a defective product. So we need to actually look at these different critical to quality characteristics and then allocate CPK in the same way we allocated reliability for the different parts of our smart lock. And when you get those slices of pie right. So remember, if we do the simple thing where we go through and just give the same goals to everything, we have a problem. And so how do we go about dealing with this problem? Well, there's 7 steps when it comes to getting these goals correct. The first thing you need to do, if you're manufacturing or producing something and it has some sort of quality goal or target overall, you need to understand everything you can, which starts with understanding your customer and how that relates to manufacturing specifications. And if there are some that already exist, do these already include margin? Do you already have a parts per million target for your defective loaves of bread? You also might have existing quality information. You might have existing information from vendors or field data or test data. Has a FMEA, especially a process FMEA, been done? Before you even think about coming up with CPK goals, you need to understand as much information as you can. Too many organizations I've been involved with, unfortunately, rush to the next steps without looking at what has already been done, and they waste precious time and precious money redoing or relearning things that have already been learnt by some people who did a really good job previously. So understand your product, understand what it means to be high quality, and look at what might have been done already to essentially process or analyze the challenges of making something high quality. Then we establish our product quality goals. Do we need to conduct quality demonstration testing, which means we might need to have confidence? Are there uncertainties? For example, you might have some CTQ characteristics, but you really don't have a good idea of how your users or customers are going to sort of prioritize each one. Sometimes you do. We've been making bread for the best part of several millennia now, so we have a really good idea of what human beings value or like in terms of loaves of bread. But when it comes to an emerging product, do you know what is too sharp or too shiny or not shiny enough or too heavy or too plastic feeling or so on and so forth? If you've got tons of uncertainties, then you might need to have a lot more margin. And of course, mobile phones or cell phones are a good one for this one. Are they likely to be used in a different application? The cell phones of today are based on the companies who had the forethought to predict that their phones would be used in different applications, and those who originally manufactured cell phones and mobile phones exclusively for the luxury market, they don't exist anymore, because we now, all of us now use smartphones, and it's just those ones who realize this, or mobile phones or cell phones. It's those early producers who realized that were the ones who were able to get through that quite chaotic start to our mobile cell phone journey. And if any of these things exist, then your actual quality needs to exceed specified quality. So that might mean that if you think your customer says, oh, I can tolerate up to X part per million, well, if you've got tons of uncertainty, then you might need to tell your manufacturing team, don't care what the customer says or what we think the customer believes, we need to exceed that requirement by a lot. And the next thing we need to do is determine the quality characteristics. So for example, what are the critical to quality characteristics for our loaf of bread? There's so many different things that matter when it comes to defining what a high quality loaf of bread is, and we can't usually look at every single one of these and monitor them with a very forensic eye. We might just say, you know what, big ones that matter the most are height, mass, and chewability. That might be because the things like taste, we know so well that if we get certain things right, it's going to taste good. But when it comes to chewability, which is based on how long that loaf of bread stays at certain temperatures and what those temperatures are, and for mass, how many ingredients get put into our mixing bowl at the very start, and height, how much our bread rises during the proofing or raising process. These might be so sensitive to any changes in manufacturing or baking that we might prioritize these characteristics in conjunction with the fact that we know customers use these characteristics to essentially judge how high quality our loaves of bread are. To say these are the three we're going to focus on. So in this case, we're most concerned about the height, the mass, the chewability of our bread. And so the next thing we need to do is borrow from reliability allocation and create allocation factors. So for example, our manufacturing team lead will get her 4 to 8 cross-functional representatives into a room, those people who know how to bake bread and know the challenges of baking bread, discuss reliability and quality challenges, ask them to anonymously rate each component or each characteristics, I should say, quality challenges from a scale of 1 to 10, where a FMEA, especially a process FMEA, if that's already been done, you might already have those numbers ready to go. She then averages those results from those different people to come up with those allocation factors we looked at for our reliability allocation challenge. And so in this case, perhaps our team of bread making experts looked at chewability and said that's going to be the one which has the most challenges when it comes to making high quality bread. That's the one that's going to have the most issues. And perhaps another thing that influences this is it might have a higher those which have higher defect severities. Now, this might sound counterintuitive, but you might want to give them lower allocation scores. Why is that? Because lower allocation scores are ones that will create higher quality targets. So if you have issues with customers saying, you know what, the mass might have a bigger impact on customer experience than chewability, well, that's one more motivation for people to give mass a lower allocation factor score. When I do that and want to incorporate both quality challenges and defect severity, I ask them to give me 2 numbers, and I simply take the allocation of the score for quality challenges and divide that by defect severity, or the average of each one. And that's how I get my allocation factors. So now I have allocation factors for these 3 critical to quality characteristics. And you can see now we are cooking, we have something. Now, once we have these 3 allocation factors, we then allocate quality goals. And the god-awful equation you need to use, and this is in the guidebook, looks like this. Essentially, the allocated goal for each characteristic is equal to one of these 2 equations. These are exactly the same thing, essentially written in different ways. And you'll have A subscript I as the allocation factor for the ith characteristic. The sum of all allocation factors. This symbol out here is actually the standard, the inverse CDF, the standard normal distribution, which essentially takes our challenges and turns it back through our bell curve, which we need to confirm describes what's going on. And because of this is a god-awful equation, here we have a equation I've given you in the guidebook, which you can use in Excel to essentially convert all your challenges all your allocation factors into this equation, including the parts per million target for your overall product. And all of a sudden, you will get a CPK value that if you say, hey, manufacturing team or baking team, make sure the CPK for the height of the bread is at least this high. The CPK for the chewability is at least this high. The CPK for the mass, the final about 3 critical to quality characteristics, that needs to be now this high. This is how this equation allows us to calculate. So let's look at this in practice. Let's just say that our head baker says that we need to have a quality goal for our bread in terms of defects, and that we can never have more than 200 loaves of bread out of every million defective. That's our target. Now, those allocation factors we came up with previously, where we sat down with our 4 to 8 experts and we averaged the scores, and it turns out that the allocation factor for the height of the bread was 3, for the chewability of the bread is 9.9, and the mass of the bread was 5.8, and they all add up to give us 18.7. And so if we look at chewability in particular, its allocation score is 9.9. The sum of all allocation scores is 18.7. What is the allocated quality goal for the chewability in terms of CPK? How do we get that? We have to solve one of these god-awful equations. These are exactly the same way of writing exactly the same thing, which we're going to get Microsoft Excel to help us out with. And so if you were to type this into a Microsoft Excel cell, you'd start being able to answer this question. Remember, our parts per million target is 200. Our allocation factor for this characteristic, chewability, is 9.9. The sum of all allocation factors, sum of alpha i's, is 18.7. And so when we put these numbers into our Excel formula, you can see this on the screen right now, it'll give us this number here, 1.29. That is the CPK we need to get for, or we need to try and, that is a CPK goal for chewability. And so let's look at the other allocation factors and the other characteristics. You can see that using this approach, chewability has the lowest CPK score, whereas the height and the mass have higher. Now, this might look like they're very close. Indeed are. But remember that chart where sorry, my headphones are having a little conniption. Remember that chart where we tried to align the number of parts per million defects with CPK values. And you remember they had that logarithmic scale where any teeny tiny increase in CPK has a huge decrease in the number of parts per million. And so even though these CPK values look very, very similar, they do involve slight changes which actually have huge impacts on the number of allowable defects for that particular characteristic. Now, chewability, the one which had the highest allocation factor, it also has the easiest or lowest CPK target. Characteristic with the lowest allocation factor was height, and it's the one that has the highest or most challenging CPK goal or target. And so now, as opposed to randomly going to a guidebook or a textbook or a standard where it says your CPK needs to be at least this, if you use this approach, then you can come up with CPK goals that actually matter to you and your team. What you don't want to do is invest time or money in chasing down unattainable CPKs. What you also don't want to do is create things that aren't nearly as high quality as your business case needs them to be, simply because you arbitrarily chose numbers from a textbook or a guidebook or a handbook and they were too low. If you get it right, you save yourself heartache, you save yourself time, you save yourself money, and you have a good idea of how much you need to invest or in achieving different CPK goals for different characteristics. Now, the sixth step is to add margin. You don't ever want to just sit there and say, just be on, have exactly those CPK goals and targets met on day one, because if anything goes wrong or anything changes, shouldn't say goes wrong. If anything changes in your production process, which it always does as your machines get old and your temperature sensors get covered with crumbs and everything else, then you automatically go beyond you automatically breach your system quality target. So the next thing we need to do is add margin. And Robert, I can see you've asked a question, and I will get back to you very, very shortly because that's a very, very good one. So let's just say we're going to add some margin. Now, those people who are from the Six Sigma cult, Six Sigma school of thought, they often talk about shift, where you have some sort of margin. In this case, they often use a value of 0.5. You add 0.5 to CPK goals, and that represents margin. In this case, 0.5. If we just arbitrarily choose 0.5, this gives you time and space to fix problems before you start failing to meet quality requirements. Now, I can't tell you what the right margin is for you, and 0.5 means a whole lot of different things to different quality processes. So, for example, if you already have a process which has a CPK, or if you have a product where you need to have an extraordinarily low number of defects in terms of parts per million, then adding 0.5 to CPKs has an extraordinary effect on how many allowable defects you're now allowed to have. So, for example, if you have a CPK of 2, adding 0.5 means that the incredibly small number of defects you're already allowed becomes incredibly small, and that might make it very, very hard to achieve. So 0.5 is just a number. You guys need to find the right one for you. If you have, you can tolerate more margin, at least in terms of CPK, when you are dealing with lower CPK values. But if you're already in the upper echelons of good CPK or high CPK, then 0.5 might be a huge challenge. Either way, 0.5 in this case simply represents or gives you time and space to fix problems before you start failing to meet quality requirements. And things will change. Everyone knows your machines, your processes, your humans will change over time. And that means you need time and space to be able to do something about it before things go bad. And so the last thing you need to do is lead and then do something. A lot of people think that we need to get our allocation factors perfect. You don't. It's not important. You try and get them as good as possible because that means you spend less time testing and adjusting, and you're closer to being on track from the very, very start. But let's just say the mass of your bread turns out to be the most challenging thing to address as opposed to chewability. Well, that means that you might then go back and essentially redo some of the math and then try and say, you know what? I'm going to decrease my CPK target for chewability, decrease my CPK target for mass and increase my CPK target for chewability to accommodate that, because I'm having so many problems with mass and fewer problems than I expected for chewability, that by simply changing that goal with that administrative flash of the pen, I'm now able to get ourselves back on track without having to spend any time or money. It just gives you some targets, gives you a path. And the most important thing about understanding or having a path is when you're not on the path. It gives you an idea that you need to do something. You either need to create a new path, or you need to do something to get back on that original path. So leading and doing something is the most important thing as well. So that finishes my conversation today, at least the formal part of it. I'm going to answer this really good question that Robert came up with. He asked, if your process does not follow a normal distribution, can you still use the standard CPK formula? And if so, do you need to change your CPK targets? That's a really, really good question. Now, there is a huge hole in the quality and manufacturing industry when it comes to non-normal distribution or non-bell curve processes. Technically, even though in this context, I have continually used CPK in terms of the number of standard deviations away from the mean, what it actually means is better expressed in terms of percentage of or the amount of deviation away from the mean. So you should be able to see on the screen right now. I'll actually go to a different one, which shows us the, I'll go back to our barely capable process. So those of you who are familiar with the bell curve know that about 60 to 70% of all blue data points, so to speak, will be within one standard deviation of the mean. About 95% will be within 2 standard deviations, and about 99.7% will be within 3 standard deviations. To correctly create CPK values or indices based on non-bell curve distributions, you actually need to drop the standard deviation entirely and instead look at the number of the amount of deviation in terms of percentage of the area under that curve. And if it's not a bell curve, it could be a wonky curve, it could be a slanted curve, a skewed curve, what have you. Now, many people get themselves tied up by continuing to use standard deviation for processes which aren't described by the bell curve. And if you have a process where, for example, it's not a bell curve, but it is, might get a stylus out. Let me see if I can start drawing, as opposed to this beautiful symmetric bell curve. It might look something more like that, might be more skewed. That happens a lot. Well, this skew curve, it will have a mean, which is going to be rightly there, but one standard deviation this way means a whole lot more than one standard deviation this way. So when you start using skewed curves or curves that aren't symmetric, you can't use standard deviations anymore. You have to start using, essentially, you have to start looking at the area which contains the middle 60 to 70%, and then the next area which contains, I know my stylus isn't calibrated to get these areas exactly right, and the next one is about 99.7%. And where those are, try and change color, where those regions then create those different sort of boundaries, you need to use them to help you work out where your CPK is instead. So in this case, we often have to use a median here. You can see that we've sort of gone 1, 2, 3 and a bit steps this way, but now we've gone 1, 2, and 2.5 steps that way. So when you convert things to a CPK using non-bell curves, you have to know what you're doing. Now, there's a whole lots of different statistical theory behind it. It's not too complicated, but suffice to say, it's beyond the scope of this conversation. To get the right CPK value for a distribution which is not bell curved. And once you do, then everything else falls into place. But what you can't do is use standard deviations in the same way you do for the bell curve. The bell curve is nice and neat and symmetric and beautiful, and if you use standard deviations for things besides a bell curve, your CPK will not have even a spiritual resemblance to the number of parts per million defects that we looked at in the chart in this presentation. Does that come anywhere close to answering your question, Robert? Thank you. All right. Are there any more questions that people might have that you might want me to answer? And I'll have this little slide up, this little chart up on the screen right now. Any questions? Any comments? Any lectures plan to deal with non-normal, like the example you gave? When you say lectures, I dare say you mean webinars. At this stage, no. Fred, we might add it to the list. Show of hands, you'd be interested in that sort of webinar in the future. All right, it's non-trivial. Okay, we might look at the order of webinars in the future, Fred. Okay, so Robert then asks, if you're calculating a CPK of greater than 10 on a test parameter, what would you advise the test engineer? So a CPK of greater than 10. Is that, can you just confirm, Robert, is that 10 or 1.0? Because 10 is an extraordinarily high CPK. 10. All right, so with that, when you're trying to calculate or characterize a CPK in general, without going into too much detail, what I always suggest, or suggest really strongly, is that you never ever do a pass fail test. Whereas if you get loaves of bread, so say a CPK needs to be greater than 10, you then test number of loaves of bread. And either then say, okay, this bread is defective or this bread is not defective, and that's it. As you can see, especially with a CPK of 10, I can't even begin to think about how fewer defects in terms of parts per million that is. I might do that. I might work that out while I'm talking to you. But what you always should do is try and get measure the chewability, for example, if that's the case. And then once you measure the chewability, then fit a bell curve or the right curve, the Y-ball log number, whatever it is, fit that curve, those number of data points, and then use that curve to calculate the CPK. You waste a lot of, it's borderline impossible to use pass-fail testing to get that sort of level of fidelity on a CPK, especially one approaching 10. So just to clarify, your CPK of 10 tells me that you're going to have, oh geez, that's not, doesn't even go that high. So that implies that you're going to have 1.5 by 10 to the power of minus 17 defects per million. That's what my rudimentary math suggests. I could be wrong in that, but that's what a CPK 10 suggests, that you're going to have 1.5 by 10 to the power of minus 17 per million, which is, as Kevin points out, extraordinarily capable. That sounds high. That CPK sounds very, very high. It seems like that would be a manufacturing process where you are all but guaranteed to never in the history of the world have anything approaching defective. And maybe that's what you need for your scenario. But it sounds like there could be my spidey senses that's tingling a little bit. Perhaps your specification limits are too far out, because if you need to be that close to your nominal value, then it makes the those specification limits almost redundant in terms of what they physically mean. But anyway, so yeah, so if you're talking, I can see you're following on from that question, Robert. So maybe the test engineer should know their test limits to try and detect process shifts better. Well, if you have a process that's that capable, whereas if where you had such negligible variation around a nominal value, at least with respect to the range between specification limits, yeah, they'll be able to detect process shifts almost instantaneously. The reason why my spidey senses are tingling is that it just sounds like and I don't know your process very well, but if that goal has been put in, you could be investing a ton of money into producing a component which doesn't need to have that level of quality, so to speak, especially if it's borderline impossible to get anywhere close to those specification limits. So you use your test limits as spec limits. Okay, so that's, I mean, there's a bigger question there to be had, and perhaps it might have to be had or discussion needs to be had offline regarding that, because there's always context, especially when people throw around numbers. Hey, we use this number here, we use that number there. You never get the context, and sometimes when you speak to people, you say, "Oh, okay, so that's why your CPK has to be that high." But my initial reaction is that seems so high that you could perhaps very comfortably drop it and save yourself maybe some money on time in your manufacturing quality. It's just hard to believe that that if on average, if a CPK of 10 essentially tells me that only 1 out of every 1.3 times 10 to the power of 23 products will be defective. That seems very challenging, perhaps unnecessarily. But I'm more than happy to speak offline if that's something you want to pursue after today's conversation, Robert. All right, let's see. Carl has asked or suggested that maybe a checklist might be helpful. A checklist for what? And then Carl then also asks more than just pass-fail criteria, several levels of acceptability depending on customer preference. So that's sort of that's a phrase masquerading as a question. I believe you're asking. I believe you're talking about what customers value more than others, what characteristics customers value more than others, I should say. And that would then come back into your allocation factors. One of the things that kills endeavors to make high quality stuff is when things get overly complicated, which is why I love allocation factors, because that's where you can sort of summarize all the stuff that you that sort of people think is going to be important. And of course, you can then change those allocation factors as you learn more about what your customers demand or how challenging these things are to create, et cetera, et cetera, et cetera, which means that you're always on track. I don't like having reams of checklists or reams of criteria you need to sort of satisfy, because that when complex processes themselves become the product. You think you're done once you've achieved or complied with the process, as opposed to you should feel like you're done once you have created a reliable and quality product. Okay, Rob, yep, got your message. No worries. Thanks for the feedback. And thanks for feedback to Patricia. Any thoughts about keeping things simple, but not too simple? Absolutely, Carl. I love keeping things simple, but not too simple. The one of the best ways to work out if your thing is how simple things need to be is we often look at these numbers and processes and equations as making a robust process, which is part of it. But if you give allocation factors, if you give CPK values to a manufacturing workforce who's very familiar with what CPKs are, and that's the only figure you give them, then what that does is simplify their day-to-day challenges. If you give really clear, concise guidance and say, look, the only thing that matters is CPK of this number for durability, so on and so forth, that makes it really, really simple. They know if they're there, they know if they're not. If you embed a margin into the CPK target, that means they know if they're there, they know if they're not. And CPK, it's not perfect, but it's not bad at really characterizing how capable your process is. And so if you can keep things simple, that's great. Now, if people are able to understand what CPK are, and if they are able to understand what they need to do to attain CPK, certain CPK targets, that's a characteristic of your organization you should leverage. And so if you can get away with just giving them a CPK number, knowing they know what it is, they know what it means, they know how to measure it, they know how to get there, and they know what to do if it goes outside windows, then you have perhaps a really simple approach to high quality stuff. But if you have a process which, satisfies a process but more than anything else, then you might then introduce confusion into those manufacturing engineers or test engineers or whoever the people you are trying to influence. So it's all about how can you help them make better decisions. Keep it simple enough for them to know what they need to do. And if they know what they need to do and the things you told them they need to do, if they do achieve those targets, and you'll guarantee that you meet your product targets, then you're good to go. Thank you, Michael, as well. The down-to-earth approach. There's only one way to approach things, and it's down to earth. If you approach things where you go off into outer space, well, you might just get there. Thank you, Carl. Any more questions? I can see we're slowly exiting the amphitheater that is this webinar as people run off to their life. Thank you, Jing Song. Of course, you have my contact details, and you have the workbook as well, which summarizes a good chunk of this. So if any questions, feel free to reach out. Any ideas for future webinars? We've got one today. I'll add it to the list. Thank you, Kenneth. Any ideas, please feel free to reach out. Fred and I often spend a large amount of time looking at each other electronically, at least going, well, what do you think we should do? I don't know. What do you think we should do? That might be simplifying the arduous process that Fred and I go through for webinar production and process and development. But hey, any ideas you guys have is greatly appreciated. Thank you, Elise. All right, team. I think thank you, Long Chun. I think we are done. So, hey, thanks for turning up. Much appreciated. And I'll see you next time you got a spare minute to attend one of my webinars. Again, feel free to reach out if there's any questions, and I look forward to our next conversation.